In this video, we're going to talk about solutions, and this is something that you guys have used in our experiments and labs. It's just we've never really gone in depth talking about it. These are your learning targets. Let's first talk about what a solution is. A solution is a homogeneous mixture. Remember, homogeneous means same throughout. And it has two parts. It has a solute and a solvent. The solute is the substance that is being dissolved. It is the lesser amount, and it is usually a solid. However, not always a solid. It can be a liquid, it can be a gas. But for us, typically it'll be a solid solute. The solvent is a substance that's doing the dissolving. It's the one usually in greater amount, and it's usually a liquid. In fact, for us, it's almost always water. Okay, but again, solvents, there are different types of solvents. There are gas solvents, there are solid solvents. Here are different examples of solutions. Air, humid air, carbonated drinks, vinegar, salt water, dental fillings, and sterling silver. These are all different types of solutions. So a solute is dissolved in a solvent to make this solution, okay? So like air, you know that air is not just pure oxygen, it's not just pure O2, it's a gas solute that's dissolved in a gas solvent. And so you know that air has a different mixture of gases, right? For liquid solutions, we carbonated drinks like soda, any of your like Monster drinks, those are carbonated, right? That is carbon dioxide solute, so gas solute, that's dissolved in a liquid solvent, and that's how you get your carbonated drinks. Sometimes there's liquid solutes and liquid solvents, and that's how we get vinegar, and that's how we also make different types of acids. The one that you are familiar with is a solid solute dissolving in a liquid solvent. And I'll be using this example a lot throughout the video today. Salt water. We dissolve salt in water all the time, right? Especially for cooking. And that is a liquid solution. Let's talk about some definitions before we move on. When we say that something is soluble, we're talking about a substance that can be dissolved in a solvent. So a solute that can be dissolved in a solvent. Like salt can be dissolved in water. Sugar can be dissolved in water, right? So these are soluble. Whereas insoluble is describing a solute that cannot be dissolved in a solvent, okay? There are three types of solutions: saturated solution, unsaturated solution, and supersaturated solution. Saturated solution contains the maximum amount of dissolved solute for a given amount of solvent at a specific temperature and pressure. The best example is Kool-Aid. So you have Kool-Aid powder, and you mix the Kool-Aid powder into water, right? So keep that picture in mind as I talk about these three types of solutions. Saturated solution, using the Kool-Aid example, would be like the perfect Kool-Aid. So you dissolved enough of the powder into the water, and the sweetness is perfect, and it's not watered down. You don't see any powder crystals in your pitcher of water. That is saturated. It has the maximum amount of dissolved solute, maximum amount of dissolved Kool-Aid powder for the given amount of water. Unsaturated solution contains less dissolved solute for a given temperature and pressure than a saturated solution. In other words, this is like your watered down Kool-Aid. You can dissolve more solute if you wanted to, right? You can add more Kool-Aid powder to your water if you wanted to, and all of that powder will dissolve. Supersaturated contains more dissolved solute than a saturated solution. So, for example, let's say you accidentally dump the entire can of Kool-Aid powder into your pitcher of water. Well, what are you going to see happening? You'll see a lot of those crystals just sinking to the bottom of the pitcher, and no matter how much you mix that pitcher, it's just that Kool-Aid powder just won't dissolve, right? It'll just remain it'll just remain at the bottom of the pitcher, and that is what we call a supersaturated solution. It has more dissolved solute than the solvent can actually hold, or than the solvent can actually dissolve. Next, we're going to talk about molarity. You actually saw this during our reactions unit. We did simple calculations with molarity. You might remember moles over liters, or moles divided by liters. So we're coming back to that. Molarity can also be called concentration, but the word concentration is more of like a qualitative word, where if we say that something is concentrated, we're saying that it has a lot of solute dissolved. Whereas if we were to say this is dilute, it's just telling us that only a little bit of solute is dissolved. So if you take a look at this picture over here, the blue represents the solute. Okay, so for example, like salt. Okay, and the solvent is represented by the pink or the purple or the smaller particle here. So solvent will be like your water. If you look at the concentrated beaker, you see that there are more blue particles in there, so more solute particles in there than there is solvent. And then for a dilute solution, you see that there's less of the blue particles, less of the solute particles compared to the solvent particles. Okay, so dilute and concentrated is just more of like a qualitative measurement. Okay, whereas molarity is an actual quantitative measurement. So molarity is equal to moles divided by liters. Moles of solute divided by liters of solution. So let's jump into our first practice problem. Determine the concentration if 4.67 moles of lithium sulfite dissolve to make 2.04 liters of solution. Well, this kind of problem is you just plug it in and solve. So we plug in the moles on top, we plug in the liters on the bottom, we divide, and we get an answer of 2.29 moles per liter. Now, in terms of units, you could write moles per liter like this, but this is also just simply capital M. So this moles per liter and capital M are the same exact units, right? So by definition, molarity is moles per liter. So again, you can use either unit. Number 2, determine the molarity if 4.783 grams of sodium chloride dissolve to make 10 liters of solution. Well, what do you notice about this problem? You should first notice that the problem is not giving you moles, right? It's giving you grams. So if we were to just put it in the right place, this is what we would have, grams divided by liters. Well, we can't have grams, right? So we have to do just a simple conversion. So I'm going to set up the fence on the side. So we have 4.783 grams of sodium chloride. I'm going to bring down the unit, grams. And because we just need to convert to moles, we're going to write moles on top. This right here is your molar mass. So in 1 mole of NaCl, the molar mass of NaCl is 58.44 grams. My like units cancel out, and in this case, I'm just going to divide my numbers to get the number of moles, and I get 0.0818 moles. So I'm going to take the number of moles that I found here, and I'm going to replace the grams with the moles. So I have rewrite it as 0.0818 moles divided by 10 liters, and you get 8.184 times 10 to the negative 3 molarity, or moles per liter. Okay, so this would be the same thing as having that decimal place over to the left 3 times. Okay, so 0, 1, 2, 3, so 0.008184. Okay, so I'm just rewriting it so that it just looks it's a little bit more convenient. Okay. Number 3, Cyclops needed to make 500 milliliters of a 3.5 molar solution of sodium hydroxide. Explain how he would prepare this solution. Now notice that the question is saying explain, so we have to write some words, but before we do that, we need to solve the problem, right? We need to know how much he needs to actually mass out. So let's set it up, and you set it up like this. You're given the molarity, you're given the volume. We don't know moles, so that's what we put for X. But what do you notice about this compared to the formula that's given? You are given milliliters, right? Not liters. So we need to we need to convert the milliliters to liters. So there's 1,000 milliliters in 1 liter. So you just simply divide this number by 1,000. So I'll rewrite it as 0.5 liters. You solve for x, and you get x as 1.75 moles of sodium hydroxide. Well, if you're in the lab, is there a way to measure out moles? No, you can't measure out moles, right? So what do you need to do? You actually need to convert this to grams, right? Because grams, mass is something that we are able to measure in an experiment. So we're going to, again, do a simple fence. This time we're going to bring down moles, and we'll write grams on top. And the molar mass of sodium hydroxide is 1 mole is equal to 40.00 grams. Like units cancel out, and in this case we will multiply our numbers and get 70 grams of sodium hydroxide. So let's answer the question. Explain how Cyclops would prepare the solution. Well, Cyclops would measure out 70 grams of sodium hydroxide and dissolve 70 grams into 500 milliliters of water. And that's how Cyclops can make a 3.5 molar solution of sodium hydroxide. Next, we're going to talk about dilutions. And when you dilute a solution, it's simply just adding water to a solution that you already have. And this way, you are decreasing the concentration. So when you water something down, you're making the concentration basically weaker, right? So if you think about like coffee, if you have very concentrated coffee and you add water to that, well, what's going to happen to the coffee? You're diluting it, it's going to taste less like coffee, and it's not going to be as strong, right? So that's basically what it is. And we did a lab in our reactions unit where you looked at 2 different concentrations. So for example, on the screen you have hydrochloric acid at 6 molar and 1 molar concentrations, and the higher the concentration, the faster a reaction went, right? So we're relating the concentration back to that, okay? So to do a dilution, this is the formula that you need to know. M1V1 is equal to M2V2. M stands for molarity, V stands for volume, 1 stands for the initial, and 2 stands for the final, okay? So let's take a look at a couple problems. Number 1, what is the final concentration if 50 milliliters of a 2 molar solution is diluted to 500 milliliters? So you want to set this up as M1V1 is equal to M2V2. The first thing that you want to look out for is, well, which molarity and which volume will pair up? Because I would say that's the common, what is the final concentration if 50 milliliters of a 2 molar solution is diluted to 500 milliliters? The first thing you want to do with these problems is figure out what is M1 and what is V1, or what is M2 and what is V2. Basically, which molarity and which volume is pairing up. So if you read this again, it says 50 milliliters of a 2 molar solution. This right here, that word of, tells us that this volume and this molarity is actually paired up, okay? So when you set it up, you write it like this. 2 molar, 2.00 M times 50 milliliters is equal to, M2 is what we're trying to find, and we have a final volume of 500 milliliters. So you multiply 50 times 2, and then you divide by 500 to get M2 by itself, and you get a molarity of 0.200 M. Now, after you find your answer, I want you to just pause and think about your answer real quick, because you want to make sure that it makes sense, right? So if you're diluting something, meaning you're adding water to your solution, you are decreasing the concentration, right? And so does your answer make sense? If you started with 2M and now you have a final answer of 0.2 M, is that a smaller number? Yeah, and it makes sense, right? Because if you're adding water, you are lowering the concentration. So it makes sense. It's just like a quick check, okay, before you move on. So in a lab, what would this look like? In order to make a concentration of 0.2 m, you would take 50 milliliters of a 2 molar solution, okay, so 50 milliliters of that, and add enough water to get to a total of 500 milliliters. And that's how you would make a new concentration of 0.200 m. Next question, how much volume of a 3.5 molar solution do I need to make 300 liters of 1.5 m solution? Well, so again, which molarity and which volume pair up? 300 liters of 1.5 m, right? So there's your molarity and volume that will pair up together. So our first molarity is actually 3.5, and we're trying to figure out volume 1. And it says that you're going to dilute that concentration so that you make 300 liters of 1.5 m solution. Okay, so we want to know how much do we actually need of our original solution. So again, you multiply and you divide, and volume is 126 liters. The last thing we're going to talk about are some physical properties of solutions. The first thing we'll talk about is electrolytes. You guys have seen this word before. We talked about electrolytes in terms of conducting electricity, and we talked about it with ionic compounds and covalent molecules. An electrolyte is any substance containing free ions that make the substance electrically conductive. So remember that the key word here is ions. And remember what kind of compounds consist of ions. Think about the word ions, right? Ionic. Covalent doesn't have the word ions, so it's ionic compounds that make a substance electrically conductive. So if we were to dissolve an ionic compound in water, so just for example, if we were to take salt and dissolve and put it in water, first of all, it'll dissolve. And at a molecular level, what happens is that these ionic compounds, when they dissolve, they will separate into their ions. Okay, so remember, ionic means that there's positive ions and negative ions, cations and anions. That's what makes an ionic compound. So if you dissolve it in water, you're going to do the opposite. You are going to separate them back into their ions. So if you look at the screen, sodium chloride, you split them into sodium ion and chlorine ion. This is sodium nitrate. Yes, sodium ion and nitrate ion. These ionic compounds are your strongest electrolytes. Because think about when you are conducting electricity, there's a positive side and a negative side, right? And that's exactly what it is, positive side and negative side. There's 100% dissociation, meaning 100% separation of ions, okay? And that's what makes it a strong electrolyte. Whereas your covalent molecules, these are non-electrolytes. They cannot dissociate. They cannot separate into ions. So for example, here you see CH3OH, this is methanol. Well, you dissolve it in water, it could dissolve, but it'll stay together, right? So I'm going to use a simulation to show you what I mean. So here we have salt. I'm going to put a little bit of, I'm going to put some salt in there, a lot of salt in there. And I'm going to do that, and I'm going to take this light bulb. And you'll see that once it hits the water, it lights up, okay? As opposed to sugar, so let's dump some sugar in there. Okay, and then let's put our light bulb in there, and it doesn't light up. Okay, let's look at it on a micro level. Okay, so here's the salt, sodium chloride. Look at what happens when it hits the water. Sodium chloride, it's split up into sodium ions and chlorine ions. Sodium ions are the purple pink ones here, they're the smaller size. Chlorine ions are the green one, or the bigger size. You see that when it was coming out of the salt shaker, oh, there's none left, but when it was coming out of the salt shaker, it was together, and once it hit the water, it completely separated into positive and negative ions, cations and anions, and that right there is 100% dissociation. As opposed to sugar, So again, coming out, it's going to stay together. Look at what's going to happen once it hits the water. Does it separate at all? No, it stays together, right? This sugar molecules are staying together. It's not separating into ions. And so no dissociation, then it won't conduct electricity, so it would be a non-electrolyte, okay? The last thing we're going to talk about are colligative properties, and we're going to talk about two colligative properties. So this is the effect of a solute on a pure solvent. So we're going to compare how properties are different for a solution versus a pure solvent, like just pure water, okay? And for these two properties that we talk about, just keep this in mind, the more solute that's in the solution, then the greater the effect is going to be, okay? So let's look at our first colligative property. First one is boiling point elevation. A solution will boil at a higher temperature than the pure solvent. So remember, solution is like salt water. You got to dissolve a solute into a solvent. So let's pretend that we're making pasta and we want to boil our water. We're going to put salt into our water before we put the pasta in, right? So why do we do this? Some of you guys might have heard that we put salt into water because it helps make the water boil faster. Well, actually, that's incorrect. It doesn't make it boil faster. In fact, it'll take a lot longer, not a lot longer, but it'll take longer to boil now the salt water. And it's because of this colligative property, okay? What happens is the solute, the salt that you dissolve in the water, it kind of creates like this barrier almost, and it's blocking the water from escaping the liquid. So you can think of it like that, and the more salt you have, the greater the effect is going to be. So for example, if you just boil just normal water, just pure water, it'll boil at 100 degrees Celsius. But after you add the salt to the water, so technically you have salt water, it raises the boiling point, not by much, but it might, now the water might boil, or the salt water might boil at 101 degrees or 101.5 degrees. It's hard to say what the new temperature would be because it depends on how much of the salt is in the water. Okay, so what's the real reason why we put salt in water before we put pasta in? It's simply to flavor the pasta. The second colligative property that I want to talk about is freezing point depression. A solution will freeze at a lower temperature than the pure solvent. So to talk about this, let's think about in the winter when we're looking forward to a snow day. So usually when the weatherman says that we have snow in the forecast, it's very exciting, but that's not the only thing that we need to look out for, right? The second thing we need to look at is the temperature. So, and I'm going to use Fahrenheit here, but we are looking for 32 degrees Fahrenheit or lower than that, right? Why? Because that's the temperature at which water will freeze. And so that's when we know that the snow will stick, and that's when we know that ice may form. Now, again, there are other factors to snow sticking, but we're not going to really get into that. But so what happens when we're anticipating snow? We usually have salt on the roads. Some of us will put salt on the sidewalks. And what is the reason for this? If you said that it's to help melt the ice or melt the snow, you're incorrect. That's not what it does. What it does is it lowers the freezing point of water. So instead of the outside temperature being 32 degrees, it has to be lower than 32 degrees in order for the water or the rain to freeze over. And so when you put the salt on the sidewalk or salt on the roads, that's what you're doing. You're basically preventing the rain from freezing until it hits like a temperature of 31 degrees or 30.5 degrees Fahrenheit. So So that's the reason why we add salt to the roads. Other reasons might be for traction, but we have sand for that, right? So again, it'll depend on how much salt is on the roads and on the sidewalks to figure out how much the temperature will go down by. And that's it for solutions.